so within FOCETA, we developed a synthesis tool that we call TEMPEST. So this was mainly developed by Stefan. This was his master thesis. And we put together a couple of slides to show you what the tool can do and how you can use it. So I will start with a bit of an introduction, and then Stefan gives you a demo of the tool. So this is the plan for today. And so all of you know that our core topic in our group in Graz is synthesis of shields. So at least with respect to FOCETA.
I think you're not sharing the slides.
Do I share the slides? Okay. So the plan for the seminar is that I give you a quick introduction about what shields are and how we construct them. And then Stefan gives you a demo of the tool and how you can use it. So the idea of a shield is that you have given a system that is very complicated and a formal safety specification.
Hi.
Πώς τη λένε? Κόλλησα. Bettina.
Hi.
Hi. So the idea is that you have a formal safety spec and you want to know if the system satisfies the spec. And you assume that the system is too complicated to be verified. And then the idea is that we synthesize from the safety specification and the model of the environment a shield, put the shield after the system, and the shield just overrides anything that is unsafe. And then if you put it together, then you can guarantee that the entire setting is safe. And the core idea behind this, why it often works, is that we consider the system as a black box. So even if the system is a learned system that has a deep neural network, because we only use it as a black box, you can still synthesize a shield because you only need the safety spec and a model of the environment for that. And this makes shield synthesis often scalable, even if you cannot do anything with the system itself. So this is always the argument if you want to do something at runtime, that you can say you can treat the system as a black box, and this gives you scalability. And the second big advantage is that you only need to model what is relevant for safety. So you can ignore everything that you only model for performance, because this is only needed for the machine learning part to get optimality. But often the MTBs, if you only model what is relevant for safety, get a lot smaller, and then you can handle them for synthesis. So we always say the two basic properties that the shield must satisfy in order to be a shield is to guarantee safety and to be minimal interfering. So this guaranteed safety we get by using correct reconstruction methods. So by using model checkers to construct the shields or reactive synthesis tools. And what you also need, what's a huge difference between shielding and runtime monitoring is you need to be predictive. So you cannot just say in the moment where something bad happened, now something bad happened. But in order to really big actions that are safe, you have to compute the latest point in time where safety can still be ensured. So basically, we compute the winning region, and all of a sudden you leave the winning region, the shield is allowed to interfere. And this brings us then to this minimal interference property, that you're only allowed to interfere if it's absolutely necessary, and then as little as possible. So that you only say if you cross the border, then the shield is allowed to interfere. And in all other cases, the shield is not allowed to interfere. And the application area we use our shields most often is reinforcement learning, because there you have a learning agent really does control that has to interact with the environment. So it always tries out actions and gets rewards and observation of the state space. And of course, it has to try out unsafe things in order to learn that this thing is unsafe. And there is again the setting where the shield can help. So you can also put it after the learning agent to override these actions by safe ones. But I think especially in reinforcement learning, it's very nice if you put the shield before the learning agent. So you have a pre-shield. It takes away all of the actions that are unsafe, and the shield can pick any action as long as it is a safe one. If you have any questions, please interrupt me at any point in time. I just forgot to say that. So in the next couple of slides, I summarize the basic idea of how you construct such shields. So you take a formal safety specification, so in some kind of LTL or whatever you want, and a model of the environment. This can be an MTB or some input-output automaton. And then you construct a game. So in the most simplest case, you just have a two-player game that is played between the environment and the system. So the environment always picks the inputs and the system always picks the output. And in this game, you have some states that you mark as bad. So they, for example, correspond to collision. And a game is played in such a way that at every time step, the system picks an input, the environment picks an input, and it's a part of the system to pick an output. And that way, the game traverses an infinite sequence of states. And then the question is, who wins this game? And the system player wins if a bad state is never visited. And then we said that the winning region are all states from which the system can enforce that a bad state is never visited. And from this, it's then really, from this, you then synthesize the shield. So what we compute is this winning region. And this winning region, if you know what the winning region is, we know what to do in order to stay safe. So if you think about what is the winning region for this example, if you start with this gray area, so with everything that is not bad, and we can see that S6 is not a good state, so it cannot belong to the winning region because it belongs to the environment, and the environment could just decide to go to the bad state. So S6 is not a good state, so it's not in the winning region. And if you now look at S5 next, you can see that S5 belongs to the system, but the only thing that the system can do is go to the bad state S6, which will lead to the collision. So also S5 is not in the winning region. And you can do the same thing for S4 again. And then you remain with a smaller set of states that are safe. And this set is then the winning region. So if you always stay within this safe region, your system is always safe. So no matter what inputs you will get in the future, the system always knows how to react with at least one output in order to stay safe, in order to stay in this winning region. And from this, basically, we then construct a shield that allows you to do anything as long as you stay inside of the winning region. So this is the core idea of shielding, is just to play a game, compute the winning region, and see that the system always stays inside of this region.
Sorry, can we ask question interactively?
Yeah, sure, anytime.
So Bettina, just want to clarify. So you are always reducing that to a safety game and go for the maximum pervasive.
Permissive winning.
I see.
Strategy. Yeah.
Okay.
So basically, this is what we're doing.
I
so
see.
the core principle, you can take any synthesis tool that you find that allows you to have access to the most permissive winning strategy. And just don't do this determination step, because the determination step then tells you for this input in this state, give this output. And if you take the most permissive one, you have a shield.
Yes, I see. And then, so the other question I have is actually in the previous page. So if you deployed it before the shielding, actually in a model-free setup, you don't have any guarantee that so you deploy it before your exploration. By the time you are learning your reinforcement, by the time you are learning your strategy, and
you mean?
Yes, so the pre-shield setup, right? So you do this pre-shield by the time you train it, but after you deploy it, you still need the shield again, right? So you cannot take it with it, because
if you want to have guaranteed safety, you have to leave the shield there.
I see.
But what you can do is, if you want that your agent learns what is unsafe,
yes,
you can give him negative rewards for all the actions that are blocked by the shield.
I see.
Because if you don't do that, you don't get any entries for these actions. So let's say in the simplest case, we have a Q table and not a neural network. These entries may stay 0, but they might actually not look that bad. And for the deep learning setting,
yes,
we have experienced both. We've experienced that if you give him negative rewards for the unsafe actions, it might be that he learns faster the task that he has to solve, but also the other way around. In a few settings, we have seen if you don't tell him anything about unsafety, because it's handled by the shield, it might learn faster. So this, you have some ideas where it could turn out that way, but it's not always clear what is the best strategy of telling the learning agent about the stuff that is unsafe that are handled by the shield or not.
But the benefit of using this in the pre-training setup is that you are able to guide the learning agent to to optimize this objective or reward, total reward, because the shield is already telling what are allowed. So you don't get surprises or surprise cuts during runtime. That's good. Or it's less likely to get surprise cuts during runtime.
Yes, but it depends hugely on the setting with respect to reward, because if the safety objective and the performance objective are aligned, you get maximal performance by staying really safe. But for example, if you have platooning and the closer you get to the other one, the more reward you get. This contradicts safety, right? So this depends a lot on your reward function.
I see.
But you can play around a lot with these things. So you can say, we come now to the thing where we talk about that it's too hard to say something is safe or unsafe. And if it's okay, I continue.
Yes, please.
And let's have more discussions in a few slides, a couple of slides, if this is fine.
Yes, please.
This is the very first thing that we did in 2018, so it's a long time ago. I hope the video works, and it does not. Let's see if it works like this. Okay, no videos. Yeah, the first thing that we did is Backman, and you know the expected results. So if you have a shield and you can guarantee that Backman stays safe, you basically need only one learning episode to learn Backman, because Backman never dies. And only has to figure out, I have to eat the nearest dots, which is really easy. So in the Backman example, learning Backman is really hard for a deep learning agent. But if you take away the safety part, so stay away from the ghost, it's actually really easy. So therefore, Backman is the nicest example for us. It's too bad it doesn't work. Yeah. So until now, we said something is safe or unsafe, and there's nothing in between. And of course, this is not always realistic. So you have to take some risks if you have a learning agent in kind of a real setting. And this is why most of the time we consider shielding probabilistic environments, so that you don't have a 2-player game, that you have a 2.5-player game. So you have your model of the environment is an MTP, like you have most of the time in reinforcement learning. And then you can say, if I have this input and I pick this action, then I might end up in this state or in this state or in this state. And then also your notion of safety gets a quantitative notion, so it's not either safe or unsafe, but it can be anything in between. And this is why we are using probabilistic model checkers as a base. So you really get the probabilities that an action is safe. And basically what we do is, you see here in this formula, you say I want to have the maximal probability that if I am in a certain state and I execute this action, that this action is safe. And you can also can either say it's always safe, or you bound it, which makes often more sense if you have probabilities, that you say you want to stay safe for the next case steps, and you want to stay safe for a probability of 80%. If not, you block it. And this is where now the thresholds comes into play. You can say either you have an absolute threshold, where say anything that leads to an accident with more than 20% or something, you block. But you could get this way into deadlock situations, because you might end up in a situation where everything is kind of unsafe and then you don't have any actions available. Of course, you could say in such cases you allow the safest one, but still is not deadlock free. What's very nice is if you use relative thresholds, that you say you always compare to the safest actions that you have available and use the threshold based on the safest available action. And this now also allows us to play around more with the shield, because you can say you have this thresholds available and you can change the thresholds on the fly. So you can say in the beginning of the learning, I let the learning agents take more risk and try out more risky things, and later on you get more restrictive. Or you can say, okay, now you're in a particular dangerous part of the state space. Now you have to be very careful in taking risks. So these are things that then really allow you to play around and see that the progress of the learning agent in exploring the environment is good enough, and the shield is not too restrictive. But this then really depends on the application of what you want to do. Yeah, and this will not work again. This is too bad. Yeah. Okay, Stefan will try to show you the videos afterwards. So the core idea of the video should have just been, now it's not just action or not action. Now you get kind of exact probability values for the actions, how safe they are, and then you see that we blocked everything that is unsafe to a certain threshold. But maybe the videos works if Stefan then presents. Another thing that we do is we typically compute the safety of the actions online. So if you only look at the finite horizon, so you only want to be safe for the next 20 steps, you can compute the safety of all available actions online. And this is especially nice in settings where you have time between the decisions of an agent. So for example, if you have a service unit that has to go along a corridor, you have basically time to do computations at the beginning of the corridor until you reach the end of the corridor. And all of this time you can use to compute stuff. So what we do is basically, if you're at the beginning of the corridor, we already think ahead. So where will I be in what position at the end of the corridor, what available actions we have, and you can analyze the safety of all available actions and then just use it as soon as you're there. So the only tricky part in that is that, of course, in the time that you use to make the computations, the other agents move as well. So you have to think also ahead. So if I'm here, where can all the other agents be in the next 10 steps that I need to get there? So this makes the computations a bit more tricky. And yeah, you can if you want. And you can make one optimization to say whenever you see a decision of another agent, you could restart the shield computation, because then you have more information available where the agent will be if you're in the next decision state where you have to decide what to do next and which action the shield should allow. So this brings us already to Stefan's part where he will show you how to construct the shields. Does anyone have any question of the concept, what we are doing and what shields are and the stuff I just talked about very briefly?
Yeah, I have a quick question. So does the shield always takes an a corrective action, but it doesn't? But can it be used in defenses against adversarial attacks, for example, for inputs, or is this a different problem to solve?
So we are doing control and not. We are not working with images, so we are not doing classification. Those are the typical adversarial attacks. I don't think there's a lot of work in reinforcement learning yet. I think I've only seen one paper that really tries to attack reinforcement learning. And this was so kind of the message there was like reinforcement learning is so not robust at the moment that you cannot really talk about adversarial attacks yet because it's not robust anyway. Okay.
So it's always on action, not on the input to the AI agent. Okay.
So what we are doing and what also other groups are doing is to try to incorporate the assumption that the inputs are not reliable, so that the inputs might be delayed, they might be noisy and all of this stuff. But really that an input is, I don't think there's work on that yet.
Yeah, I think it's a different problem to solve. Yeah, okay, that's fine. Thank you.
I got a question about the online sharing. You ask you share the deep reinforcement learning for one step or for several steps. For every single step, you give a safety index or several steps.
This depends on how you model it. You could say that one decision of the agent kind of decides for a sequence of actions. And this computing it online only makes sense if you already decide for a couple of steps for the agent.
Yeah.
So that you have kind of a higher level thing that matches to several actions in a sequence, because you need time for computations.
Yes, I mean, for example, a trajectory have like 10 steps, and you verify each step, or you just verify at the beginning and give the results for the whole trajectory.
Yeah. So this is basically what we do, is to decide already what is safe for the next 20 steps and let him do that.
Yes, but you verify each step, or you just verify at the beginning and you give the result for the.
We verify it at the beginning. So we basically say, if you're in this state and you take these actions, does there exist a sequence of actions that you can take such that you stay safe for that and that threshold? So this is why there's written Pmax. So you assume that in all of the following states, you will do the safest thing possible.
Mm-hmm.
And for the agents, for all of the other agents, you have some kind of probabilistic models how they will behave.
So
you can either consider the other agents adversarial or probabilistic, and depending on the model that you have from the other agents, you compute, if I do this action, and afterwards I always take the safest thing possible, how safe is the one action?
Okay, thank you. Let me ask about another question about the input of the shield and the input of the actor neural network is same. Is that same?
Is what?
The input of the shield and the input of the neural network, the deep reinforcement learning algorithm is observation. So that's same.
Yes.
Okay. Thank you.
Okay.
Can I have one more question?
Yeah, sure.
Okay, so for these two-player games, which is really turn-based, I assume that you model the learning enable the agent and also the environment in some way, yeah, maybe as transition system or something. So could you comment a little bit on that?
We modeled it really turn-based. So it's always first the turn of the environment and the turn of the system. So basically, we model the environment as an MTP.
Okay.
Something more about it?
So my idea was to give you a demo. So I wanted to basically describe how we model.
Okay, perfect. Then
you will see a complete example how the modeling works in
okay.
a minute with Stefan. So
Sure,
I just wanted to give you the high-level idea, and Stefan now will really show you one concrete example how we modeled it.
Okay. Then I'll come back maybe later.
Right.
Thanks.
If I manage to share. Share screen. Okay, so you should be able to see my screen now, hopefully, and hear me through Bettina's laptop. Okay. So I wanted to give you a live demo of Tempest, and I want to basically start with emphasizing that this is for the probabilistic environment. So Tempest is a synthesis tool for shields in probabilistic environments. So we do not have this approach that Bettina exemplified in the slides, but we use dynamic programming to compute the probabilities to satisfy the traces with more and more length through iteration, and then decide for each state and action pair whether what's the probability to satisfy the property. And since I was asked to give a live demo, I just wanted to go through what some input files could look like. And since you've just asked how we model the input, I wanted to start off with something which I think is quite nice and legible. So the idea is to have a modeling language, which we call PRISM, because this was sort of the first, as I'm aware, probabilistic model checker, and they've defined a modeling language. And sort of my example that I use to convey the idea on how we model these things, I use sort of a warehouse. So this grid that you can see here should be a warehouse where, yeah, the hash symbols are walls or shelves, and we've got two robots moving within that warehouse. And in the case here, where we have a stochastic multiplayer game, the adversarial robot, the second one, gives us, yeah, it works in an adversarial way. So it's trying to crash into us. And the idea to model this is to describe some constants which give us the space where we discretize the environment, and some other constants. And the main idea is that each of these robots have their coordinates, and these coordinates concatenated as vectors basically give us one state of the environment. So the XY coordinates of robot 1 and the XY coordinates of robot 2 concatenated with some Boolean that tells us whether robot 1 or robot 2 is currently has its turn to move. And the idea is to sort of have a breadth search algorithm to from the initial state, which is defined by the initial values each of the variables in our state space can have, and then try to search all possible transitions to get the whole state space. And I hope this is somewhat legible here. So these robots have their XY coordinates, and whenever they the coordinates match to what we call a guard here, the robot can then increase its X or decrease its X value, which means that it moves to the east or to the west. And the modeling language gives us the possibility to describe these formulas, which hopefully make it clearly understandable. So a robot can move to the east or to the west if it's not between some shelves or in some kind of open row. And this is basically what describes the environment. And the first thing that TEMPEST does is, from this description, given the initial state, it will traverse the whole state space to know or to build up the model. And what we then combine it with is a list of properties. So we build our model once, and then iterate through a list of properties and basically run a model checker, which will compute the probability of satisfying the property in the initial state, but on its way, it will compute it for each and every state in the model. And while computing the probability for each state action pair to satisfy, here in this example, not crashing within the next 6 states, we basically extract these intermediate results and then construct a shield from it. So let me show you that. Let's see. So this should take just a few seconds, which will present us then with the different post-safety shields that I'm constructing here. And I guess, yeah, it's not taking that long. So what we're doing here is we are creating these post-safety shields for different values of lambda, so different values of restrictiveness. And what we will end up then with is some text files, which are basically lookup tables. So one of these post-safety shields basically tells me if the robots are in these positions, if my robot wants to move to the east, I'll let him move to the east. And in the beginning of the model, the robots tend to be far apart, so you don't really see any deviations here. So basically, the robot is basically free to do what he wants in this case here. Okay. And now I actually wanted to show you the difference to one of the other shields. So this is really a kind of a small example. So I had a look to get some differences. But if we decrease the lambda value to just a quarter, we can see that in some cases the shield says that, okay, staying within that row of the grid world is okay, but if I'm very, very restrictive, I say, okay, the probability of crashing into the other robot is too high, so completely move away. Which we can see here that the 0.9 shield is more restrictive because it overrides more of the actions. Okay, and I started with the game model, but we are also able to model things in MDPs. And I started with the game model because I think the MDP thing is way more bloated, but I hopefully still understandable. So in this case here we have robot 1. Yeah, does anyone have questions so far? Okay, if not, then I'll continue. So the idea here is that we have the same model with this warehouse, just that the other robot now is not controlled by some adversary, but it has to it's moving randomly, which means that we have to define way more of these guards in order to have the robot correctly move within the system. And this basically results in the same shields, just that here in this case we're not expecting the environment to behave adversarially, but randomly. Okay. Now I wanted to quickly round this up with some more examples. So what we're currently doing is we're trying out a Q-learner in combination with automata learning to construct an abstraction of an environment. And I simply wanted to show this to show you how TEMPEST would look like in one of these frameworks or loops where the learner is already involved. So this looks way less legible, but we have once again a grid world that you can see on the left, where the ego or E tries to reach a goal, but it should not run into these D or def states. And we basically use automata learning to get such an abstraction and construct a prism MDP model out of this and have TEMPEST compute a safety shield, which should keep us from running into the def states with high probability.
The grid world is slippery.
You
have to mention that.
Yeah, I have to mention that. Yeah, otherwise that would be.
So if you tell the robot go right, it might actually go up or down with a certain probability.
So that's at the very bottom of that. So all of these states here, thanks, I would have totally missed that. These states that have an integer label here are slippery and based on that map that is below. So whenever one of these labels is too near to one of the def states, the shield should prevent going there or taking the wrong action when in such a state, in such a slippery state. And what I wanted to show here is the difference between these lambda and gamma shields. So we now have another difference. We now have one of these pre-safety shields. So the shields that I've shown you for this warehouse example basically tell the agent, if you would have taken that action, take the other action. And the pre-safety shields give you a list of allowed actions. And I wanted to show you the difference between these lambda and the gamma values. So I've let this run, and we're basically comparing the two shields here. And we can see that, for example, in location 31, the best performing or the action with the highest probability to stay safe has a probability of 0.83. Where on the bottom you can see that moving to the left only has a probability of staying safe of 75, and if we take the absolute, well, the absolute of 0.7.5 is lower than 0.8, so this gets cut away. What we can also see here in this example is that in location 32 and 33, the probability of staying safe is 0 for any action that I can take. So in the absolute shield, this basically would result in a deadlock. That's why these lines are missing here. Okay. And for my last example, I wanted to show you something which is way different. And just so that I mention it, TEMPEST is also able to do qualitative things, quantitative, sorry, yeah, thanks. Which I don't want to go too much into detail, but just so that I show you some other example where the robot is moving around. But what we also did is we abstracted a model of a junction where cars arriving, and the shield's task is to balance out the distribution of the waiting cars. So we are penalizing whenever the difference between the waiting cars at the north-south lane and the east-west lane is too high, and so we can use shields to also correct actions for such quantitative.
Okay, so just to mention here, so Stefan now made a huge jump.
Yeah, I made a huge jump. Yeah.
Everything we talked until now are safety shields, so they tell you how safer actions. And he now made a huge jump to something we have never mentioned before, so that you can also use them to minimize costs. So that you say that you have some costs in your model, that models some performance costs, and the shield checks that the costs don't get too high. So this maps to mean payoff games, so that on an infinite run, the costs will not ever get too high.
Yeah, I just wanted to mention that so that, yeah, you can see that we don't have all these robot grid worlds, but something else as well. Yeah. This concludes my demo. Do you have questions?
Yeah, can I ask a question? It looks to me it's still only simulation. When you considering like hardware implementation, is it expensive to add the shield? For example, if it take extra time for the action and maybe more power consumption.
I don't know exactly what you mean, that you take really models of hardware circuits?
Yeah,
Model
I mean,
cameras, what do you mean?
When you're considering like implementation at this kind of model into the hardware, and whether your shield will take extra time for the inference.
So if I understand correctly, your argumentation is nothing ever takes no time, and if the shield interferes, this takes time.
Yeah.
And it should be modeled.
Yeah.
So we are working with Kim Larsen on synthesizing shields with UPAL so that you have timed automata models. And there we kind of model really intervals that a certain action is only valid for this interval, and if you interfere, this also costs you time. But it's still, I would say, far away from any real world or real hardware near implementations that you say you really consider hardware implementations and model them very fine. But this timing expect is a valid expect that we kind of totally ignore in the setting. So everything you do costs no time. And this is of course not realistic.
Okay. Thank you.
Okay. Do you want to? Maybe this is a good thing to follow up. Should we discuss that? So this was one of the videos that Bettina wanted to show beforehand regarding the online shielding. Do you want to discuss?
So you have two learning agents that learn to play snake. So they should collect the apples while avoiding to get eaten by the other snake. And this is normally completely fluent. And here you see very nicely what I meant before. So you have the time between two corridors to compute how safe the next actions are. Sorry. Okay. And the next one is the more interesting one. So in Stefan's laptop, it looks completely fluent. It just doesn't look very nice over the internet. Can you stop now?
Sorry.
Stop. So you have seen in the beginning when the snake comes down, and you model the purple snake in a way that it's equally likely that the purple snake goes left or right. You cannot say in advance which side, so they're both same as bad. But as soon as the purple snake decides to go right, you can restart the shield computation, and then the shield switches to going to the right is bad and going to the left is okay. So basically, whenever an agent makes a new decision, you can restart the shield computation, you have more information, and then you can give a more finer safety analysis, and this is what we do in these examples. And the new results might arrive in time before you need it, might not. You can also show the traffic videos if you want.
Yeah, I guess that was too much of a jump there.
But now you already talked about it.
Yeah, I mean, we've got enough time. Let's see.
So we have one more video if you like. Just because Stefan mentioned these performance shields, could also show you videos to that. But, so we had a reinforcement learning agent that controlled like the inner city of Helsinki, so they controlled all the traffic lights at once. I'll go a bit further, like in a minute or so.
Oh, this is true. Okay.
So and this traffic light controller works fine, except if something happened that was not expected by the traffic light controller. So like there's a traffic jam at the highway, does not continue anymore. And then the reinforcement learning agent does not work nicely anymore. And this is basically then where the shields take over. So you see on the left side that the shields start to interfere so that the traffic more goes on the side roads. And if you would continue, so if you go back at the end of the video. So you don't see it nicely in the simulation, but after a few minutes, you have a traffic jam on the right side for 1 or 2 kilometers, and on the left side, the traffic is still totally fine. And this is now so basically performance and not safety, because the shields try to balance on how many cars are waiting at one road and what would it cost the shield to interfere, because interfering with the learning agent costs something. So we assume the learning agent is very cool and you should not interfere all the time, but also what does it cost you if you don't interfere now and don't change the traffic light and get even more cars waiting? And yeah, so I think that's it.
Yes.
I have a question. What's the difference between the tools Prism, Storm, and Tempest?
Okay, so Tempest got its name from Storm, basically. So Storm is what we've built Tempest on. So all of the model checking algorithms implemented in Storm are basically what we use in Tempest.
So Storm cannot solve games.
Yeah, okay.
So there's Prism and Prism games. So Prism was extended to Prism games to be able to solve probabilistic games, and Storm was not. And in Prism, there was not really any nice way to extract the strategies. So you have seen very nice strategies that tell you this action safe for that and that and that thing, so that you have this most permissive winning strategy in the end that you can use as a controller. And basically Storm, so Tempest just extends Storm also by these game algorithms that also have Prism games, but you can use the strategies in such a way that you have a shield out of it. You know what I mean?
Yeah, that makes sense.
And additionally, so for safety, it's basically just you use the strategy in a different way and you can print it. And so Tempest, so the real thing that you cannot do in Prism games is this solving mean payoff games. And yeah, but I thought this goes too far if I explain you how we do shields for performance. Maybe we should have done it, but this was basically the main selling point of the tool, was to be able to solve mean payoff games and to combine this with safety also, so that you can say you are performant and safe. And this is what we are currently working on, that you can say it's very important for you that you have guarantees that some performance measures are met and you are safe. But this is still work in progress.
Okay, thank you.
May I ask a question about the shield? The input of the shield, that means you know everything of the environment, is that right? For example, it's fully white box, right?
So at least you say you have a model that is correct, that is faithful, and that models everything that's relevant for safety, if you talk about safety shields. And of course, this assumption is very, very idealistic and often not realistic. So we have papers where we combine shielding with techniques of model refinement and model repair and all the stuff that you say, you monitor the environment, and if you see that the model of the environment is not correct, you repair the model and synthesize a new shield and replace the old shield by the new shield. So yeah, the entire shield computation depends on you have a correct model.
Okay, I see. Thank you.
So this is kind of combining model-based approaches with the reinforcement learning doesn't have a model, so that you have the strength of both. But this is the huge problem, that you can only use a shield if you have a model. Stefan mentioned in one sentence before that this example he showed you with the grid world, so this should be the first try to use kind of combine automata learning with that gives you a model with shielding. So use automata learning to get a model, then compute a shield, and this goes in a loop. But that you need a model is the limitations that they have for shielding.
Okay, so that means your shared method is not available to apply in partial observable deep reinforcement learning, right?
In partial, yeah. So you could use a POMDB as a model to construct a shield, but we all know that it's not scalable. it would be very, very, very interesting to look at cases and what we can do there. So you have an idea. So a grid scenario where we could work with clever abstractions so that we could still handle this. And computer shield for this would be very interesting, very nice.
Okay.
So to have shields for partial observabilities. And we want to look at this for a long time, but I think you really need a concrete scenario, a concrete use case where you start working with it and that makes sense and where you then have proper abstractions so that you can handle it.
Mm-hmm. Yeah. Yeah, I agree. Okay, thank you. Thanks for your answer.
Any more questions?
Guess not.
Okay, at least stop the video recording.